today we're going to cover the KKT conditions. This is our last week on optimality and duality. And then to remind you all, you guys have a homework due on Friday, I think. Can somebody confirm that? Is that right? Homework due on Friday. And then next Monday, so a week from today, will be the little test. I guess we could spend a few minutes discussing it now. I was trying to think whether it's worth discussing it now or Wednesday. We can spend a few minutes discussing it now. So the format is going to be just true or false questions or multiple choice questions. So kind of like the quizzes you've had so far. And it's not supposed to be very hard. I'd say it's supposed to be about the level of the quizzes, maybe a little bit harder than the quizzes, which means that if you came to lecture and you kind of followed the basic concepts, the little test should be fairly straightforward. I'm aiming for about 30 to 35 questions, and you guys have 80 minutes to do it. And they're, like I said, they're true, false, multiple choice questions. So I don't think there should be time pressure. These things should be like, convex function has a positive or a negative second derivative everywhere in R. That might be, for example, a question. So they shouldn't take you like 2 minutes each, I don't think. And you're allowed one sheet of notes, so front and back. You're allowed one sheet of notes as a kind of study sheet or whatever. And it's going to be inclusive through this week, so everything up to everything up and including Wednesday's lecture. In previous years, we used to have midterms in this class. I've decided this year to change that. So this is going to be in place of the midterm. We're going to have 2 little tests, one now and then one at the end of the semester. You may have heard from previous years' cohorts that the midterms were hard or something. It's not the point of this little test. This little test is supposed to be straightforward. Any questions? Okay, great. So that will be on Monday. And we have, as usual, 5 office hours, or maybe even 6, I think. We have a lot of office hours each week. I don't know how many we have. We have a lot. So if you are wanting to ask questions to help you study for the little test, then come to some of our office hours. So the KKT conditions is going to be what we talk about today. I'll just remind you about last time we talked about duality. Some people call what we learned last time Lagrangian duality. So in case you hear that word, it means what we learned last time. It was the idea that we, started with an arbitrary minimization problem, not necessarily convex, just one in a generic form for the moment. And we formed something called the Lagrangian, which was a function of our primal variable x and dual variables u and v, where these were defined to have one component for each of the constraints in our primal problem. And we essentially lift these into the criterion by multiplying them by the dual variables, these constraint functions. Okay, so it's the sum of ui hi plus the sum of vj lj plus f. That's the Lagrangian. And we think about the Lagrangian as having an implicit domain with u being non-negative in every component because it multiplies an inequality constraint with hi being less than or equal to 0. Okay, so we define this Lagrangian, and then we define the Lagrange dual function by minimizing over all x, not just feasible x, all x, the Lagrangian, at a dual point uv. Okay, so this is a function of uv, and it's defined as the minimum of the Lagrangian at that uv over all possible x. And there's this nice relationship that we get between this dual function, say, and the optimal value of this program. This dual function for all u and v, for which u is positive or non-negative in each component, serves as a lower bound to the optimal value in this primal optimization problem. And if we were to maximize over all u and v, then it gives us the tightest lower bound possible. And it's the optimal value of this program, which we call the dual problem. It still lower bounds the optimal value of the primal. Okay, so this is what we said right here. It's always true that the maximum of the dual function overall, u that are non-negative, that's the dual problem's optimal criterion value. G star is always less than or equal to f star, the optimal value of this original program. That's called weak duality. And another thing that we learned last time, we in fact proved, it was just a couple lines, was that this dual problem is always convex because this g function is always concave. So we're maximizing a concave function subject to a linear constraint. That's always a concave maximization problem. So we also, just kind of per our nomenclature, our normal nomenclature, we call this a convex optimization problem as well. Okay, and then the last kind of very important thing we learned was that strong duality holds in a very broad sense for convex problems when the primal is convex, and specifically under something called Slater's condition, which just asserts that we must be able to find a point x that satisfies all the equality constraints and all the inequality constraints strictly. If this is satisfied, this is called Slater's condition, then under the additional assumption that the primal problem is convex, we get strong duality. Okay, so we get F star equal to G star, not just this weak relationship. Okay, and importantly, we can even only ask that these inequalities are strict over the non-affine constraint functions. So if you have affine constraints, all you need to do is find an x for which it satisfies all the equality constraints. So these must be affine, right, if the problem is convex. This is a bunch of equality constraints. And it makes all the affine inequalities hold, not necessarily strictly, and it makes all of the non-affine inequalities hold strictly. That's also a sufficient condition for strong duality, provided that the problem is convex, primal problem is convex. Okay? Any questions about that? Because that's going to, these last two slides are going to be very crucial for what we learned today, KKT conditions. Yeah? Good question. Probably. I'm not sure I could give it to you off the top of my head. The way that it's proved in the Boyd and Vandenberg book uses kind of the epigraph representation of a convex problem. So most of the way that some of these fundamental things are proved are to convert the problem into a problem involving sets. And somehow this means that the set, the feasible set has a non-empty relative interior. If you just were to look at kind of the equality constraints, the subspace in which those define, the feasible set's not empty. So I think it's a very innocuous condition. I can't imagine very many primal problems being interesting that don't satisfy this. But I'm not sure I could give you great intuition. I could think about it and get back with you. Yeah?
If you have a non-convex problem, you take the dual, and then you take the dual of the dual, how does that relate back to that? Because that would be convex, right? Does that relate to any discrimination between non-convex problems?
It's a good question. So, I mean, maybe I should just bounce that question back off you. So if we take the primal criterion value, right? And I have a non-convex problem, then I'll probably get that weak duality is strict, right? So what happens if I take the dual now of the dual? So the dual is a maximization problem. It's convex, or it's a convex optimization problem. So where would G star star lie with respect to G star? It would be bigger than or equal to, right? Because we're providing an upper bound now. So in general, it's not really clear where that's going to lie, whether it's going to provide like a lower bound. Right? We do have this relationship. So I'm using this to mean the dual of the optimal criterion value of the dual problem of the dual. Maybe it's not great notation, but it's not really clear where this is going to lie, right? So sometimes you can work out the dual problem exactly, even if the primal problem is non-convex, in which case you can probably work out the dual of the dual exactly, because this would be convex, and so you can actually maybe construct such a relationship and kind of compare them. Sometimes it provides you with a useful bound, but in general it's not clear. It's a good question. Other questions? There's a neat example in the Boyd and Vandenberg textbook, which I had in the notes but I took out, that you might want to look at, that constructs the dual of a non-convex problem for which the problems have integer values. So it's an example of a problem where the primal is non-convex. It has integer constraints. I think they're even binary, actually, on the variables, but you can derive the dual explicitly. So it's a pretty neat example. Okay, so today we're going to talk about the KKT conditions. Go through a bunch of examples, address this idea of problems which we can express in constrained form and Lagrange form, which we see kind of all the time in statistics and machine learning. And then if we have time, I'll go through an example application of the KKT conditions to prove something kind of interesting. Okay, so the KKT conditions, like duality, are very simple in a sense, and all the arguments that we're going to be using in today's lecture are very simple, but I think at least they're very profound. So, a bunch of really simple arguments lead to something quite powerful. So we're going to be looking at the same kind of general form optimization problem, not necessarily convex. Okay, of course we'll kind of pay, special attention to that. And first we're just going to state the KKT conditions. The KKT conditions are a set of 4 conditions, okay, that associate with a particular problem like this one. We're just going to state where they are first, and then we're going to kind of work with them and see how they relate to optimality. So the first of the 4 KKT conditions is called the stationarity condition. And these, by the way, stand for Karush, Kuhn, and Tucker. I'll mention them in a little bit. The first asserts that if we were to take the Lagrangian as a function of x, so this guy is a function of x, okay, and we were to fix u and v at just some values, that the point x must lie, if I take the subgradient of the Lagrangian at the point x, then that must contain 0. Okay, so the KKT conditions apply to a triplet x, u, and v. And the first condition is that if I were to look at that u and v, evaluate the Lagrangian, think of it as a function of x, and take the subgradient, then I must have 0 as a subgradient at the point x. Okay, so you can think of this as saying that x minimizes the Lagrangian, right, at the point u and v from our subgradient optimality condition. If I were to look at uv, treat the Lagrangian as a function of x so that u and v fixed, x minimizes the Lagrangian. The second condition is called complementary slackness, which says that this triplet I'm looking at, I must either have the ith inequality constraint being tight at x, so this must be actually equal to 0, or the ith dual variable u being 0. Okay, so their product must be 0, which means that if this inequality constraint wasn't tight, if I had hi of x strictly less than 0, I must have the corresponding dual variable being equal to 0. And the last 2 conditions are just primal and dual feasibility. So I must have x that meet all the inequality and equality constraints, and I must have u being non-negative in each component. Okay, so this is a set of 4 conditions on x, u, and v, and we're going to see that actually, in a very broad sense, they are equivalent to having an optimal primal solution x and an optimal dual solution uv at the same time. Okay, so if x, u, and v satisfy these 4 conditions, then in a very broad sense, that's equivalent to having x that solves the primal and uv that solves the dual. So let's prove that. Let's just go through each direction and prove that. So let's cover necessity first. Okay, so this is the direction that says that if I had primal and dual solutions, then this actually implies the KKT conditions. Okay, so any x star, and I'm calling it u star, v star, that are optimal must satisfy the KKT conditions. However, we're making kind of one relatively important addendum, which is that we're looking at primal and dual solutions that have 0 duality gap. Okay, so these are solutions, and more than that, we're assuming that actually the primal criterion value at its optima is equal to the dual criterion value at its optimal. So this is implied, for example, by Slater's condition if this problem was convex. Okay, so of course we know that that's enough to ensure strong duality. Okay, so let's suppose that we had x star and uv star, and we had 0 duality gap. We're going to now show this implies the KKT conditions. So the first thing we're going to do is we're going to say that actually, just by definition, f at x star is equal to g at u star v star. This is strong duality, right? With there's 0 duality gap here. Okay, but by definition, right? By definition, the dual function at any point u and v is equal to the minimum of the Lagrangian at that uv, right? It's equal to the minimum over all x of just the Lagrangian. Say Lj of x. Okay, and here I'm just saying that I'm asserting that this also must be true at u star v star. Of course, this is true for all uv by definition, so it's true at u star v star. Okay, so that's why we have an equality here. Okay, how about this next line? So this next line says that, well, of course, the minimum over all x of the Lagrangian at u star v star must be less than or equal to what happens at x star, right? Because just by virtue of the fact that I'm minimizing, I can't make the Lagrangian any smaller than what it is here. So in particular, it's less than or equal to its value at x star. Okay, but because of the fact that this is feasible, right? So u star is a solution, so it must be feasible, which means it must be non-negative in each component. And x star is a solution, so it must be feasible, which means this must be less than or equal to 0. And by this same argument, Lj of x star must be equal to 0, right? And we're looking at solutions, so of course they have to be feasible. We know that this whole term is less than or equal to 0, and this whole term is equal to 0, which means that this thing is just less than or equal to f of x star. So we've established through a very simple chain of inequalities, right, that f of x star is less than or equal to a bunch of stuff, which is in turn less than or equal to f of x star. So what we get out of that is that actually these all must be equalities. In particular, these last two steps must be equalities, not inequalities. Okay? Any questions about this sequence of arguments? Yeah? No, because you can see I'm actually, maybe it's clear if I just were to write it like this. So this is all I'm saying. So this function, treated as a function of x, is less than or equal to the value it takes at any x, right? So I'm going to plug in x star. Sorry, the minimum of this function is less than or equal to the value it takes at any x. So I'm just going to plug in x star. Okay, so you can see I've replaced all appearances of x by x star. Good question. Okay, and just to remind you, the first thing holds by definition of g, the dual function. This holds by this argument, and the last thing holds by the fact that u, v, and x must be feasible because they're solutions. So for the argument we've seen many times, this whole thing is less than or equal to 0. Yeah, another question. We didn't need to use Slater's condition, but we needed to use strong duality. So we needed to have the fact that the primal criterion at its optima is equal to the dual criterion at its optima. So that could happen, for example, for a non-convex problem, in which case this would go through. I just was saying that you can think of this as, for example, happening for primal problems with strictly feasible sets or whatever, Slater's condition. Okay, so let's now let's look at the implications of the fact that these must all be equalities. So I'll say it in words first. The first thing, okay, we can see actually the fact that this is equal to the minimum, it tells us that x star must minimize the Lagrangian at the point u star, v star. That's exactly stationarity, right? So the fact that we have an equality here means that x star achieves the minimum over all x of the Lagrangian at u star, v star. That tells us that the stationarity condition must hold, right? I take a subgradient of the Lagrangian with respect to x, that must have 0 in it. Okay, that's just subgradient optimality applied to the fact that x star minimizes the Lagrangian. Okay, so that told us that stationarity holds. How about here? Okay, so the fact that these two are equal tells us that actually this whole term must be 0. Right? This term is already 0 because we have feasibility of x star. This whole term must be 0 because these two are equal. Well, this is a sum of terms, each of which is bigger than or equal to 0. So actually each term must be 0. Right? They can't cancel each other out because they all have the same sign. So now each of these terms has to be 0, which that actually is complementary slackness. Right? So now we've just shown that complementary slackness must hold. And primal and dual feasibility, well, we get those, of course, for free. I mean, if we have solutions, they must be primal and dual feasible. Right? So to wrap up, this is just what I said out loud. The first inequality implies complementary slackness, the fact that this is an inequality. And this inequality, the fact this is an inequality, this one implies stationarity. This one implies complementary slackness. Primal and dual feasibility hold. by the fact, we have optimal solutions. So what we've just shown is that if you have primal and dual solutions with zero duality gap, then this triplet, X star, U star, V star, must satisfy the KKT conditions. Okay, in other words, we've shown necessity of the KKT conditions under strong duality. Okay, let's do the other direction now. Let's do sufficiency. So we're going to now suppose that we have a triplet, X, U, V, that satisfy the KKT conditions. And we're going to try to prove that they're optimal, that X is optimal for the primal problem and UV is optimal for the dual problem. Okay, the argument's also extremely short. So X, U, and V satisfy the KKT conditions. Let's just go ahead and use complementary slackness. Okay, right off the bat, because we know that that's one of the four conditions that they must satisfy. So at the point that we're looking at, U star and V star, right, we know that these X star, U star, V star satisfy the KKT conditions. We know that actually this thing is defined by the minimum over all X of the Lagrangian at U star, V star. But stationarity, right, tells us that that's achieved at X star. Okay, and that's just that first line, writing out what the Lagrangian is. So we actually know that the dual function at U star V star is equal to f of x star plus the sum of ui hi plus the sum of vj lj. And now let's just invoke, for example, complementary slackness and say that, well, the product of ui and hi at x star must be 0 for every I. That's complementary slackness. So this whole term is 0. And, well, part of the KKT conditions is feasibility. So, for example, this thing must be 0 for each j, right? Lj of x star. So this whole term is equal to f of x star. And now we've just shown that we have the primal and dual criterions matching at U star, V star, and at x star. That implies optimality for both pairs, right? We argued that at the end of the last lecture. If you ever have a zero duality gap, that implies that you have the solutions. You must have both the optimal primal solution and the optimal dual solution. Okay, that's always the case, as soon as you manage to make these two criterions match. Okay, so what we've just shown through maybe just two or three different lines of thought was that if X star and UV star satisfy the KKT conditions, then you must be looking at optimal primal and dual solutions. Okay, so putting that all together, what we've just shown is that the KKT conditions are always sufficient, right? There was nothing here that assumed convexity of the problem. The KKT conditions are always sufficient. So as soon as you satisfy the KKT conditions, you can say that you have the optimal primal and dual solutions. And they're necessary under strong duality. Okay, so if you have strong duality for your problem and you have solutions, then they must satisfy the KKT conditions. So one way to remember this kind of equivalence then is that suppose you're looking at a problem in which you know strong duality holds in the first place. Okay, for example, it could be a convex primal for which there's a strictly feasible point, x. Then the KKT conditions are equivalent to having optimal primal and dual solutions. Okay, x star and UV star being primal and dual solutions that's true if and only if x star and UV star satisfy the KKT conditions. So we just proved that over the last couple of slides. Okay, let me pause for questions because very simple arguments, but it certainly can be tricky. So I want to make sure that we can all be on the same page. Yeah. Do we have a dual equivalent for stationarity? Not really, right? So, I mean, if you were to form the Lagrangian based off of the dual criterion, then, well, let me see if I can. I mean, it's true that this is always true, right? Somehow. I mean, these lines I just wrote above, I guess I'm writing the exact same thing over again. So the KKT conditions tell us that this is true. Right? The first thing is true by definition, but this is true by stationarity. I don't see how that obviously implies something about UV star being optimal with respect to some formulation of the Lagrangian. Certainly if you form the Lagrangian according to the dual function, they would have an analogous property. Right? And you could think of the dual variable for the dual as being x, so you could write down an analogous property. But I don't know that I could write down something involving the Lagrangian of the primal that was like this. The dual has constraints. The dual has at least a non-negativity constraint. But it also typically has more constraints because these are kind of implicit in the function g. So remember when we did linear programs, for example, we got a bunch of equality constraints that appeared through definition of the function g. Okay, other questions? Okay, so let me pose a question. So I said the KKT conditions are always sufficient. So does that mean that you can now all of a sudden solve a bunch of non-convex problems? Right? All you need to do is make these true, and then you have a primal solution in X, and you have a dual solution in UV. So why isn't it easier then to solve non-convex problems? All you need to do is satisfy these conditions. True. Well, which of these four conditions is hard to work with if we have non-convex functions in our primal? Stationarity, right. So, for example, for a smooth problem, you can think of stationarity as just taking the gradient of f and the gradient of hi and the gradient of your equality constraint functions and taking a linear combination set that equal to 0. Okay, when these are convex, it's also kind of typically easy to write down subgradients of your functions. It's not always easy to satisfy this, but at least you can write down the stationarity condition. If some of these are non-convex, then it may be very hard to calculate the subgradients, or they may not actually have subgradients. Okay, so that's usually the bottleneck in using the KKT conditions for non-smooth problems. So that's why I have this warning here. So warning about the stationarity condition. For a differentiable function, we cannot use this idea that its subdifferential is just the set containing its gradient, or the only subgradient at f of x is the gradient, unless we know the function is convex. So that's not true in general. So if you had a smooth non-convex problem, the stationarity condition could still be very hard to work with. Okay, so that's what somehow makes the KKT conditions most useful for convex problems, right? Because we can write down the stationarity condition. And that's why I've posed it in this way. You could think about it as essentially being a necessary and sufficient condition for optimality in convex problems. Okay, in non-convex problems, things are, as always, more kind of complicated. There's always a wrinkle. Okay, and you actually will see this presented a little bit differently in Boyd and Vandenberg. I think this, in my opinion, this is a clear way to think about things. They present things a little bit differently. They don't actually even use, there's no appearances of subgradients at all in that book, so of course they have to present things differently, but you'll see things phrased a bit differently, and hopefully it doesn't throw you off. There's nothing contradictory about the way we learned it and the way that's presented there. It's just they present things in terms of gradients. Okay, so I think it's kind of interesting or fun just to take a second to talk about where this name came from. So in the Rockefeller book, if you read the Rockefeller book, he'll refer to these as the KT conditions, Kuhn and Tucker. And that's because for a long time that's how these conditions were referred to in optimization, named after Kuhn and Tucker, who are both very, very famous kind of optimization giants. And they published these in a paper in 1951. Much later, so I don't even know what year. I mean, Javier would be able to tell us. I think my guess is sometime in the 90s. People found out that there was a master's student called Karouche who had these same conditions in his master's thesis in 1939. So he actually had the same kind of idea as Kuhn and Tucker. I guess this would be 12 years earlier. And people didn't really know about it because this master's thesis was unpublished. So now we call them the KKT conditions, and we put Karouche at the front to give him, to acknowledge him. So you'll see these called the Kuhn-Tucker conditions if you're reading a paper that's old enough. They won't include Karouche. So for unconstrained problems, these KKT conditions are nothing more than subgradient optimality, right? If we had no constraints in the primal, then essentially none of these appear because we have no dual variables, right? So none of these appear at all. And primal feasibility, of course, whenever you have a solution, you must have it being feasible for the optimization problem. So that's just kind of implicit. And these don't appear either because we have no dual variables. So we're just saying that the subgradient of our function f at the point x must contain 0. We must have a 0 subgradient. So that's what we already learned, right? To minimize a function f. That subgradient optimality described, was equivalent to having a minimizer x. So sometimes you'll see people calling subgradient optimality the KKT conditions. I even do that somehow absent-mindedly. We just write down a function, take its subgradient, set it equal to 0. Sometimes I say that's the KKT conditions. Well, it is, but it's just a very simple version of it. One thing to note also, when we learned subgradients, I said that actually those could somehow also characterize optimality in constrained problems. The idea was to somehow put the constraints into the criterion and then use the fact that we know how to take subgradients of indicators via the normal cone. So that's another way to actually derive the KKT conditions, and Rockefeller goes through this in detail. We could have started off by saying that I'm going to add indicators for all my constraints that are inequality constraints and equality constraints, take a subgradient of that whole thing, set that equal to 0 at x star, and try to come up with a set of conditions for when this is true. We would arrive at the KKT conditions, okay, if we worked with these normal cones. I think it's just much more complicated in general to think about this, so the KKT conditions, I think, are easier to work with and easier to remember. So let's do a few examples. Let me see how many examples I have. I think we have a number of examples, so we can do a couple and then take a break. So the first example we're going to do is minimization of a quadratic subject to equality constraints. And we're going to see this pop up again when we talk about Newton's method, or at least I think we will. Javier is going to cover that unit, so I imagine he'll talk about this. So we're going to be looking at problems of this form, often in Newton's method, but it's also interesting just in its own right to ask, what's the solution to a quadratic subject to an equality constraint, quadratic criterion subject to an equality constraint. And we're going to think about Q as, of course, being positive semi-definite, which makes this problem convex. So we have a convex problem. We have no inequality constraints. So let's just write down the KKT conditions one at a time and see what we end up with. So I'm going to, well, first I guess I'll write the Lagrangian. Sometimes when I write the KKT conditions down, I don't actually write the Lagrangian. I just kind of look at stationarity on the fly. So you take a derivative of the constraints, add those to the criterion times dual variables. But we can start off by writing the Lagrangian explicitly, if that's helpful. Okay, so that's the criterion, and we're going to add U transpose AX, okay, to the criterion, because these are our equality constraints. We have no inequality constraints. And so what does stationarity say? Okay, actually, even before we list the conditions, let's just back up and say this is a convex problem, because I told you Q was positive semi-definite. It is strictly feasible because we have no inequality constraints, so Slater's condition definitely holds, right? And of course, there's a point that makes AX equals 0. I can just take 0. So therefore, the KKT conditions are necessary and sufficient for optimality. So once I write these down, satisfying the KKT conditions is going to be equivalent to solving this problem. So stationarity, we have to say that if we were to take a subgradient of this with respect to x, that must contain 0. But everything here is differentiable, right? So I can just take a gradient and set it equal to 0. So stationarity says that qx plus c plus A transpose u equals 0. It's got that by taking gradients here. Okay, complementary slackness. There's nothing there because there's no inequality constraints. And primal and dual feasibility. Well, there's nothing for dual feasibility because I have no inequality constraints. So I don't need u to be non-negative in each component. I can just have it be arbitrary. And primal feasibility is just that I must have ax equal to 0. So now we know that if we could satisfy these two conditions, right, both of these simultaneously for x and u, for variables x and u, then x is going to be the primal optimal solution, and u is going to be the dual optimal solution. It's pretty neat, right? Because it's very simple. In fact, it's just a single linear system in x. We can write this as follows. Q times A transpose times A times, sorry, not times. These are blocks of a matrix. Q, A transpose, A, 0. I'm defining blocks of a matrix. This whole thing times the block variable xu must be equal to, see if I got this right, minus c 0. So all these four together are equivalents to just this single linear system, right? Because dual feasibility and complementary slackness were empty, they were trivial, and primal feasibility and stationarity I actually can write as just one single linear system. So q times x plus A transpose times u must be equal to negative c. That was stationarity. And then primal feasibility is just A times x plus 0 times u must be equal to 0. Just ax equal to 0. So I just have to basically solve this system for the variable xu, right? For example, if this was invertible, I just invert this matrix, multiply by minus c 0, and that gives me the primal and dual solutions directly. So this is sometimes called the KKT matrix. You'll see it called the KKT matrix for exactly this reason. So it came out of the KKT conditions. Okay, it's very useful because, well, this problem is not one that you can obviously solve in closed form, right? We can pretty much write this in closed form. Just write xu is equal to this matrix inverse times this because of the equality constraints. Right? If you didn't have the equality constraints, then you can just take the gradient and set it equal to 0, quite straightforward. With equality constraints, things are obviously not, way more complicated, but they're certainly more complicated. And what we see from the KKT conditions is that actually we can still write down a single linear system and use it to solve for x, as well as the dual variable u. Okay. Let me just maybe give you a tiny bit of motivation. So how does this show up in Newton's step? Well, in Newton's method, we always make quadratic approximations to our function, and we minimize these quadratic approximations over and over again. So at the kth iteration in Newton's method, this q is going to be like the Hessian, right? At let's say the point x k minus 1. And this c is going to be like the gradient at the point x k minus 1. Okay, we made a quadratic approximation to our criterion of this form, where the q and c are defined in terms of the second order Taylor expansion of our function. And this is how we usually think about Newton's method. Minimizing a quadratic approximation over and over again gives us an update direction for that, based on that. If we had equality constraints in the original problem, so if I was actually minimizing, let's say, some smooth function f of x subject to ax equals b, then I would want to make sure that in performing Newton's updates, that I maintained feasibility, that these equality constraints were maintained all the way through. So what we usually do is we usually say you start with a point, you initialize with a point such that the equality constraints are held. And then remember, this is actually solving for the update direction, not necessarily for the next iterative, the update direction. I maintain that the update direction, let me call this D. So my optimization variable here is D. Whatever I add to x, I maintain that it must satisfy a times d equals 0. So that if I was feasible at iteration k minus 1, that if I move x in the direction d, it's still going to be feasible because the equality constraints would continue to hold, right? Because a times the quantity xk minus 1 plus any scalar multiple of d would still be equal to b, what I wanted it to be. So this is the kind of canonical problem that we would solve in Newton's method with equality constraints. And the way that we do it actually is just to form this thing called the KKT matrix and take a step based on this linear system. Just a preview of what's to come. Okay, I don't know that I want to go all that carefully over this water filling problem, but we can maybe go through it somewhat quickly and then take a break. There's more details in the Boyd and Vandenberg book. I got this example from the Boyd and Vandenberg textbook. So it's just a neat example in which the KKT conditions actually pretty much give you the solution to a very non-trivial problem. The problem is to minimize the negative sum of logs of xi plus alpha I, where alpha I is a constant. That these are just given to you before you solve the problem. And you can think about this thing as the communication rate of the ith channel. So they give some kind of information theoretic explanation of this. And I want to essentially allocate some amount to each of, let's say, n channels in a way that makes communication as best as possible. So x is a vector that denotes how much I'm allocating to the ith channel and its ith component. So it has to satisfy these constraints. I'm just kind of making sure that let's say it sums to 1 and it's non-negative. And really think about it as proportions that I'm assigning to each of n channels. So this problem, we can look at the KKT conditions for it. And the first thing I've written up here is just stationarity. But I've done so in a way that kind of writes down the Lagrangian implicitly and then invokes stationarity. So remember, the Lagrangian is gotten by adding, let's say, the sum of minus ui xi and the sum of vi times 1 transpose x minus 1 to the criterion. I take the constraints and I add them to the criterion multiplied by dual variables. And here I'm differentiating that with respect to x. So the Lagrangian was minus the sum of log alpha I plus xi minus the sum of ui xi, because these were actually less than or equal to 0. So I've flipped the sign of the constraints before I've defined this term, plus v, just one equality constraint, right? This is just one equality constraint here. So that's the Lagrangian as a function of x, u, and v. And now stationarity has me differentiate this with respect to x and set it equal to 0. Okay, again, everything here is smooth and convex, so I can do that. So the first term, right, if I differentiate with respect to, let's say, xi, right, for each I and set that equal to 0, I get just minus 1 over alpha I plus xi. This term just gives me minus ui, and this term just gives me v, right, because this is just the sum of xi's. And then these are everything else that you'd usually see, right? Complementary slackness, just ui times xi must be equal to 0. X is bigger than or equal to 0, sums to 1, and u is bigger than or equal to 0. So if we can satisfy these conditions, right, for any x, u, and v, we can satisfy these conditions, then we have solutions. We have the primal solution in x, and we have a dual solution uv in u and v. So the first thing that we might think about doing when we see this system of equations we're trying to solve is to eliminate u. Okay. we can, for example, eliminate u just by this first equation. So ui in every component must be equal to minus 1 over alpha I plus xi plus v. Okay, and so that turns complementary slackness into this, right? I've substituted in for ui. And then that turns dual feasibility into this. Okay, u being bigger than or equal to 0, remember ui was equal to minus 1 over alpha I plus xi plus v. So that being larger than or equal to 0, it's just asserting that this must be less than or equal to v for each I. So we've used stationarity to eliminate u, and then we've just rewritten the other conditions in terms of u. That's all we've done. So now we only have to solve essentially, right, for x and v. And you can directly look at this problem and argue that complementary slackness and stationarity imply this relationship between xi and v. Okay, I won't go through why that's the case. I think it's straightforward, but it doesn't. This is somewhat of a specialized example, so I don't think that learning this all that carefully is going to translate into being able to solve different problems. But if you're curious, you can take a look at that example in Boy and Vandenberg. So it turns out you can just directly look at this and assert that u and v must satisfy a much simpler closed form relationship. Kind of like something like thresholding, where if v is bigger than or equal to 1 over alpha I, then xi must be 0. Otherwise, xi is 1 over v minus alpha I. Okay, so we can write everywhere xi as the maximum between 0 and 1 over v minus alpha I. In other words, it's the positive part of 1 over v minus alpha I. And then just looking at the feasibility condition for x, we can solve for v directly, right? Because this is the sum of the x's must be equal to 1. We've already reduced x to be a closed form function of v. The sum of the x's summing to 1 now just gives us a single equation to solve for v. So the KKT conditions reduce down to a very simple univariate equation, right? Remember, v was a dual variable that multiplied the equality constraint. We only had one equality constraint. So solving for this is just one-dimensional convex optimization. Okay, and when you get down to one dimension, you can pretty much do whatever you want. You can throw down a bunch of grid values. You can evaluate the criterion at each one and look at which one is smallest, right? In one dimension, everything is pretty much doable. So once you solve for, let's say, 1 over v, then you get the solution, the primal solution directly from this. Okay, and there's a nice interpretation that you can get in solving this in terms of water filling. That's why it's called the water filling problem. Okay, so I went over that kind of quickly. I think I just wanted to give you an example in which the KKT conditions sometimes reduce a very complicated looking problem into one in which there's a kind of very simple avenue for solving for the primal variable. This happens every once in a while. In my experience, it doesn't happen all that often with kind of interesting problems. So that's why I said this is rather specialized. But it certainly can happen, right? The KKT conditions take you down to a very nice, like, let's say, one-dimensional equation you have to solve for. Okay, let's maybe take a break before we do support back to machines, and then we'll come back and finish off with the examples. Example. Somebody raised a very good point, which I'm actually embarrassed because Christoph, your TA, raised the same point last year, and it's taken me a year to fix the typo, and I haven't done it. So I'm sorry about that, and that's a bad typo. The stationarity condition is supposed to say this. Okay, 0 is in the subgradient of the Lagrangian at the point x given u and v. Now, that's what I've written down is somehow equivalent to this, provided that f, hi, and lj are all convex. Right? Because for convex functions, the subdifferential of a sum of functions is the sum of their subdifferentials. That was one of the first rules we learned. For non-convex functions, I cannot take the subgradient or subdifferential of a sum and assert that's the same as the subgradients, the sum of the subgradients. Okay, so one example is, for example, think about adding, say, the absolute value of x with negative the absolute value of x. Okay, this guy has no subgradients anywhere, the negative absolute value of x. So if I look at the sum of their subgradients, that would be empty, right? Because I'm trying to take sum of everything in one set, sum of everything in the other, but one thing doesn't have any elements. Whereas their sum is actually just the 0 function, right? And that thing has subgradients 0 everywhere. So for non-convex function, let me just repeat, you cannot necessarily move, right, this del operator inside this in the sums. So this is supposed to be the stationarity condition the way it's stated. We're supposed to just be thinking that x minimizes the Lagrangian at the point u and v. This is exactly the Lagrangian. This thing is defined to be Lagrangian, so this is the way you should be thinking about it. Okay. Important only when we're talking about non-convex problems, but still, it's not good to have, you know, this typo here. Okay, so thanks for reminding me of that. Any questions about that? So let's talk about support vector machines. The KKT conditions are actually, I think, fairly useful and interesting for support vector machines. And I may be somehow doing a few parts of your homework by going over this, so maybe I'll try to, you know, if I can remember some parts we asked you to solve, I'll try to be vague about what I say here. But this is a kind of interesting interpretation that you get for support vector machines from the KKT conditions. So remember, let's say we have points that are labeled either -1 or 1 in associated features or predictors. And the SVM problem is a QP which tries to find essentially a hyperplane that separates all the points labeled -1 from all the points labeled +1 with the largest margin as possible, okay, allowing for some slack. So this is the picture you might have in mind. So the hyperplane is defined by beta transpose x plus beta 0 equals 0. So let's say this space is RP, and x is a p-dimensional variable. So this is hyperplane is defined by beta transpose x plus beta z equals 0. Or we're going to solve for beta and beta 0 through the SVM problem. On this side, the hyperplane is defined by beta transpose x plus beta 0 as positive, and this side is defined as being negative. Okay, and so we're trying to separate these points. Some are labeled +1, like these guys. Some are labeled -1, like these guys. You're trying to find a hyperplane that separates these two groups of points with the largest margin as possible. In fact, the margin ends up being 1 over the norm of this vector beta. It's the relationship, one of the two norm of this vector beta. It's the relationship in support vector machines. And we're allowing for some slack. Okay, so here, what happens if we just had this constraint yi transpose xi plus beta 0 being, let's say, bigger than or equal to 1 without these slack variables? Well, that would be asserting somehow that, first of all, every point yi must be on the right side of the hyperplane, right? Every positive point must be on the positive side of the hyperplane. Every negative point must be on the negative side of the hyperplane to make that product positive. And bigger than or equal to 1 is saying that actually it must be not only on the right side, but it must be outside of the margins. So if we could solve this problem with all the slack variables being equal to 0, then we'd have established perfect separation of our two classes, right? And the margin would be actually 1 over the norm of beta. With these slack variables, we're allowing for that not to be true for every point. Okay, that we can still have a little bit of slack. That's why they're called slack variables. So we could have points lying on the wrong side of the margin, like for example these points, because we assert that the product of yi and xi transpose beta plus beta naught has to be bigger than or equal to 1 minus psi I. And if psi I is, say, positive, then that's actually putting us on the wrong side of the margin. That's allowed by the support vector machine solution. And if psi I was big enough, we could even have, right, the point being on the wrong side of the hyperplane, like this guy here. Okay, so I just wanted to give that setup because we're about to discuss somehow the implications of the KKT conditions, which involves this picture. So maybe that was review. Hopefully that was review. You guys learned that in 701. But if not, that was a refresher. So let's now take the KKT conditions for this problem. So first we can write down the Lagrangian. So our primal variables are these guys. And our dual variables I've called W and V. W and V. I'm trying to figure out which one I used for which. So it looks like I used V for psi. So W and V. So we get it by taking the criterion. And adding the dual variable times the constraint. So here I'm going to flip the sign of these guys. So I'll do minus the sum of vi psi I, and then minus, actually I don't think I need to flip the sign here. I'll just do plus the sum of wi times 1 minus psi I minus yi times xi transpose beta plus beta naught. Okay, that's our Lagrangian. And stationarity, we take the, everything here is smooth again, so let's take the gradient set it equal to 0. But there are three kind of parts to our variable, primal variable here, right? So we have to take the gradient with respect to beta, beta naught, and psi, and set this all equal to 0. So the beta block, let's do the beta block first. We get beta, none of this contains beta. This one contains minus the sum of wi times yi times xi. Okay, this thing must be equal to 0. That's the beta block of the stationary conditions. How about beta naught? So for beta naught, we actually only have yi times wi, the sum of that times beta naught appearing in the criterion. And beta naught only appears, see, as a linear term here, so that tells us that the sum of yi times wi must be equal to 0. That's the beta naught block of the stationarity condition. And for psi I, it's actually 3 terms. So let's just do it for one I. So we get C minus Vi minus Wi equals 0 for all I equals 1 through n. So those are the stationarity conditions. Okay, just gotten by taking gradients. And I've written them here just rearranged. Beta must be equal to the sum of yi, or wi, yi, xi. And this I've just written in vector form, okay, by introducing the vector of all ones. W must be equal to C times the vector of all ones minus V. In complementary slackness, okay, well, we actually have two terms from complementary slackness, because we have 2 inequality constraints. So we can think of this in 2 parts. The first part is complementary slackness for this constraint, which says that Vi times psi must be equal to 0 for all I. And the second is this inequality constraint, which says that Wi has to be, it's either this constraint has to be tight, or Wi has to be equal to 0. Okay, so how do I get rid of this thing? Didn't want that. So either this has to be tight, or Wi has to be equal to 0. That's complementary slackness for that other constraint. That's actually a very interesting kind of assertion for support vector machines. Why? Well, look, W is the dual solution, or it's one part of the dual solution, and beta is a part of the primal solution. But beta is really somehow what we care about in terms of the hyperplane. Okay, it determines the orientation of the hyperplane, also determines the size of the margin. This is obviously important too, but it's just an intercept. Right, this tells us just kind of where to shift this hyperplane. So beta, we can see from the KKT conditions, this is already interesting. We can express it as a linear combination of dual variables, the sum of Wi, yi, xi. So if we actually knew how to solve the SVM dual, we wrote down the dual last time, right? If we solved the SVM dual, then this is how we'd get the primal solution out of it. We get it like this from this relationship. Okay, already kind of interesting from the KKT conditions. More so than that, though, is that actually we can see that the primal solution is only ever somehow determined by points for which the dual variable is not 0. Right? If wi was 0, then the point yixi would have no effect whatsoever on the primal solution beta. Okay, so I'll say that again. Points for which wi is non-zero are the only points that actually matter in determining the primal solution. Those things are called support points. And we can see that, for example, when the slack here is loose, right? If this slack is loose, if we actually have a strict inequality up there, that forces wi to be 0, which turns that point into a non-support point. So it actually doesn't matter at all in terms of defining the solution. So here, I'm just repeating what I said. At optimality, we have this relationship. wi is non-zero only when this is true. Okay, it's only non-zero when this is true. And these points are called the support points among the data set. That's hence the name support vector machine. So points for which we actually have an equality in this constraint are called support points. So let's think about somehow two cases for support points that have to do with this picture. So support points are ones for which this is actually an equality, right? The slack variables really matter for these. So let's think about two cases of the slack variables. If the slack was actually 0 at the point I, then xi lies on the edge of the margin, right? So it's a point like this. It's classified appropriately, and it lies on the edge of the margin. Okay, remember I said that if we had yi times, beta transpose xi plus beta not equal to 1, then it would be basically saying that points lie in this margin, and bigger than or equal to 1 is they lie on the right side of the margin. The slack variables allow that not to be true by pushing us towards the decision boundary. But if the slack variable was 0, then we actually have a point that lies on the edge of the margin. Okay, so support points that have 0 slack actually lie on the edge of the margin. They are important for defining the solution. And the dual variable can be anything in between 0 and c. Okay, you can see that because this being 0 means that vi can be anything, right? Which means that the dual variable can be anything between c at the biggest and getting very close to 0 at the smallest. For a support point that's non-zero, then this lies on the wrong side of the margin. Like for example, this guy. Okay, lies on the wrong side of the margin, or even this guy lies on the wrong side of the decision boundary, right? Because now this slack is positive. It's this amount. For such points, we actually know that the dual variable must be equal to c for those points. So they kind of have the biggest effect in terms of determining the primal solution, right? They have the biggest effect from determining the primal solution because their dual variables are as large as possible. And how do we see that that's the case? Well, if this was non-zero, it forces vi to be 0. When vi is 0, you can see that w must be equal to c based on the stationarity condition. Okay, so I think a pretty nice relationship that we get out of the KKT conditions for support vector machines. Now, it doesn't really give us a way to find a solution explicitly, but I think it gives us a better understanding of the structure of the solution, right? This whole idea of only some points mattering in the data set. The data set is kind of only used in a sparse way in order to determine this hyperplane. And in fact, there's some very nice work in the last, let's say, 5 years, which uses the KKT conditions, arguments like this, to screen away points from your data set that you know are not going to be support points before you even solve the problem. Okay, if you had, let's say, 1 million data points and you wanted to classify into 2 classes, if 900,000 of them you knew were not going to be support points, then you wouldn't have to even include them in the SVM problem. Right? Because if you knew somehow when you did include them, the dual variables would be 0, then you wouldn't have wanted them in there in the first place, right? Because it's just kind of adding extra dimensionality to your problem, and they don't affect the solution at all. So if you could say ahead of time that a bunch of points were going to be non-support points, you don't have to even include them in your SVM optimization. That actually is incredibly helpful in terms of computation. So there's some nice work that are on stuff that are called screening rules, which get rid of points a priori before you even solve the problem, that you can kind of prove are not going to be support points. And they use arguments very similar to this, just based on the KKT conditions. Okay, we have a couple more examples of the KKT conditions. I think I'll probably go through this one and just state the last example, but there's a question, yeah. Yeah, that's right. The screening rules don't follow from the KKT conditions. They're not just following from this logic, but they certainly use these properties, these relationships between W, V, and beta. Yeah, screening rules I think are pretty interesting. They are, they're not really that complicated in principle. It's just that to get better screening rules, you need to do more complicated stuff. So if you wanted a rule that got rid of some support points, we could probably come up with a pretty simple one, but if you want to make sure that it's somehow as tight as possible, then they get sophisticated. We may cover them as an advanced topic. There's interesting screening rules not only for support vector machines, but also for the lasso to screen out features before you even solve the problem there. Okay. So let's go through this in detail, and then we'll just state the last property and not prove it. So oftentimes in statistics and ML, we go back and forth between kind of two different forms for problems, right? The one form that looks like this, minimize f of x subject to h of x less than or equal to t, and Lagrange form, minimize f of x plus lambda times h of x. And we think about, in each case, there being an associated tuning parameter. Okay, that tuning parameter being called t here, and this tuning parameter here being called lambda. And we often claim these are equivalent. Like if you wanted to solve one, well, you could just solve the other, and it would just correspond to a different value of the tuning parameter. You see that all the time. And we're going to now assert that's actually true almost all the time, just based on a very simple argument with the KKT conditions. I'm kind of worried, though. Did we assign this as a homework problem? Did we end up not assigning this as a homework problem? Is this on the current homework? Can you guys be honest with me? Is this a problem on the current homework? We don't know? Okay, well, I'll take your word for it for the moment. I thought that we had maybe assigned this, but then I left it in the slides. So it doesn't matter. We'll go through it anyways. We'll give you guys a freebie in case it actually is in the homework. So let's actually go both directions. Let's go from the constrained problem to the Lagrange problem. Sometimes this is also called penalized form. You might see this also being called penalized form. So if this problem is strictly feasible, let's assume that f and h are convex. If this problem is strictly feasible, then strong duality holds, right? That's Slater's condition. If I can find an x for which h of x is strictly less than t, then I get strong duality. And that means that there is some lambda. So here I'm calling lambda the parameter associated with this constraint. It's the dual variable associated with this constraint, such that any solution in this problem, x star, must minimize the Lagrangian at lambda. So what's the Lagrangian? It's just this, right? F of x plus lambda times h of x minus t. And so because the KKT conditions, right, are necessary under strong duality, I know that the primal solution must also minimize the Lagrangian at lambda. And look, t is just a constant here, right? So that's the same thing as saying that x minimizes f of x plus lambda times h of x, which means that it's a solution in the Lagrange version of the problem for that lambda, whatever the dual solution happened to be at that lambda. Okay, so now we've just shown that for every constrained problem, there's a corresponding Lagrange problem that has, solutions of the constrained problem also being solutions of the Lagrange problem, right? Let's go the other way around. If you have a solution in the Lagrange problem, then you can go to the constrained problem, and you can check that the KKT conditions are satisfied by taking the bound, t, that tuning parameter, to be equal to just the achieved value of the of this function h, which we usually call the penalty in this problem, the penalty term. you can check the KKT conditions are satisfied. That's a very straightforward kind of two-line check. And maybe just in case this is on the homework, I'll leave that out as a safety. You guys can check this part. So the conclusion is that, well, actually, we said that any solution in the Lagrange problem, as I look at different values of the tuning parameter lambda, those are always solutions in the constraint problem at different values of t. That's always true. That was just this side, this direction right here. The flip direction was that if I look at solutions in the constraint problem for which I actually had strict feasibility, with which I had h of x being strictly less than t for some x, not necessarily the solution, just some x, those are all solutions in the Lagrange problem. So it's almost a perfect equivalence. We can almost always say that we can take a problem like this and go to a problem like this. The only time that breaks is when I'm looking at a version of the constraint problem for which I don't have strict feasibility. Okay, so if I'm ever at a version of the constraint problem in which I don't have strict feasibility, there may not be a version of the Lagrange problem in which the solutions to that constraint problem are also solutions to the Lagrange problem. Okay, that's the only time in which that's not true. But even that you can kind of finesse. So, for example, if the only value of t that leads to a constraint set that's feasible but not strictly feasible is t equals 0, then we do get a perfect equivalence. You just take lambda to be infinity there. Okay, let's suppose that this was a norm, for example. When I set t to be equal to 0, I don't have, let's say, a strictly feasible constraint set. Well, in that case, I can just set lambda to infinity, and I get a perfect equivalence between these two. Okay, so even somehow this, I think, usually doesn't really matter. Another example is if h is a non-negative function, then you pretty much have a perfect equivalence between the two. Okay, so that was maybe just an assertion that some of you guys have been doing or seeing a lot is valid. We just use the KKT conditions to prove the equivalence between those two. Very last thing. We're not gonna go through this at all in detail. I just wanted to make you aware of it. I think also it's on your quiz, so it's probably good to say it. It turns out we can use the KKT conditions often to prove things that are surprising about convex problems, and here's an example of one such thing. So let's suppose we're looking at a problem of this form: minimize f of x beta plus lambda times the L1 norm of beta. And f is a strictly convex function, but I'm telling you nothing about x. Nothing about x whatsoever. So x could, for example, have 100 rows and 100 million columns. So it's certainly the case that x transpose x is singular. And f could be, for example, the least squares loss. Right? So that's strictly convex, but as soon as I think about how it acts on beta, this thing is not a strictly convex function of beta. So that's the setup we're considering. So if I think about minimizing, say this problem, which would be the lasso problem when I have squared error loss, right? Or it could be like logistic regression with a lasso penalty if I chose this appropriately. If I'm thinking about minimizing this criterion over beta, then according to what we kind of know just generically from convex optimization, this may not have a unique solution, right? Because the criterion is not strictly convex as a function of beta, because this matrix X, let's suppose, is very wide. Okay, the KKT conditions we can actually use to prove that we only get non-uniqueness in kind of very pathological situations in this problem. So it's almost always the case that we get unique solutions. And the condition that we need on X is a condition that's called general position. And if X has entries that are drawn from a continuous probability distribution, then that's always met. So with probability 1, there's a unique solution. And it has also, at most, min NP non-zeros. So this is proved in the next kind of several slides. It's not terribly difficult proof, but I think we just are running out of time. So I'm happy to go through that in my office hours if you guys are curious. Again, the implication is that the lasso problem pretty much always has a unique solution, even when X is very, very wide, as long as its entries are kind of continuously distributed. And if you had a problem with 100 rows and 100 million columns, so 100 million variables, that's 100 observations, then the solution, in the case that it's unique, it has at most 100 non-zeros. So it can't be supported on very many features. It's another kind of property of the lasso. Okay, that was it. See you guys on Wednesday.